Okay, so today it will be another lecture which will be mostly about theory of methods of imaging, when we will cover the basics of CT and MR. And if we have some time left, we will just do a super quick Python notebook about opening image volumes instead of planes. Then we will switch more to the image analysis side, more laboratory from the next lectures. So we were left from the last lectures with 2D planar X-rays. And this is the images that you get. And we said it's a projection that compresses all the volume around a single direction. And I want to ask you, can you spot anything here? Probably you should be able to. This is a relatively easy case. And you can see some kind of shade here of a mass, and in a more difficult way on the lateral projection. Now, this is what you get if you have if you were able to get a volume. So instead of projecting all the intensities together and lumping all the 3D information in 2D, if you are just able to slice them, to slice the volume, you can take a whole volume of the body, slice it every millimeter, every 2 millimeters or so, and then you can identify structures much more easily without anything potentially obscuring what's along the way. So what's the intuition between a CT? We have seen the shade of an object along one direction and the other. The intuition between them is that if you take really lots of angles, you should be able to reconstruct all the volume, because in every projection you say, okay, this object is to the left of this one when viewed in this direction, but it's on the right of the other one when looking in the other way. And so in this way they invented what's now called CT, and which means computed tomography, and which was originally called computed axial tomography, or CAT scan. Here's the history. In 1917, there was a mathematician which came up with the idea of this paper with this strange name of a purely theoretical invention, which relates an image to these projections, which it's what we said before. You have projection along lines, and these are the views that we have along each angle. Some 50-something years later, Godfrey Hounsfield and Alan Cormack built the first physical actual CT scanner, and 8 years later they got the Nobel Prize in Medicine for this invention. A couple of years later, we went from this axial scanner, which we'll see the definition in the next slide, to the spiral scanner, which means that it can acquire the whole volume in a single take. In the early days, you could acquire one slice of volume in 4 minutes, which take a whole rotation. And you could reconstruct an image which was as small as 80 per 80, and you had 8 levels of bit intensity. No, sorry, 3 bits intensity, which means 8 gray levels. So it wasn't really that good. Nowadays, this is 2002, but nowadays we have marginal improvements because the technology is already quite advanced. You could have a rotation in 0.4 seconds. You could acquire up to 16 slices in parallel. Now you can acquire also 128. And you have an image with high resolution and a high gray level intensity. So this is an image of the first CT scan ever. This is a brain, or maybe we should use the term head, because with this level of resolution we can just distinguish the bone from the non-bone, not really the intricate structures of the brain. It was called the EMI scanner because the EMI, the music company, had so much money from the Beatles that they decided to start building medical equipment. And so EMI founded the development of CT. And these are the properties. It had a single slice. So you had a detector and an X-ray tube rotating. And it was acquiring all the data in one slice, which was, let's say, 1 centimeter thick, half a centimeter thick, depended on how you collimated the beam. But so it was not a volume, it was a slice. Of course, when you acquire a slice, you can also then acquire a second slice, move it another time, acquire a third slice, and so on and so on. By the way, to reconstruct this very small image, it took 30 minutes of computing time. You see the name is computed tomography because there is no way to do that analogically. You need some algorithms to go from what the detectors acquire to a visible image. So this is the difference between the CT, between the axial and the helical scans. The helical scans moved as I just described. You acquire one slice, you do a rotation, then move the table where the patient is lying down, acquire a second slice, and so on and so on. With an helical scan instead, you have the bed continuously moving while the X-ray tube keeps on rotating, so you can do it simultaneously. Of course, you need an X-ray tube that is capable of producing lots of X-rays in a very short frame. Then you need a detector that is able to read that, which means not only the detector, but also the front-end electronics. You need a lot of bandwidth to do that. And then you need a table with a super precise movement and some mathematics which can be fixed. This is the interior view of a CT scanner. This is the X-ray tubes, which emits conically X-rays starting from a single spot. They are collimated so they do not go outside of where it's needed. And they move along straight lines, going from the tube to the detector, which is in front of all these fans that cool the electronics. Then the whole system keeps on rotating. You need to keep in mind that in modern days, the X-ray tube of a CT scanner, which might need to dissipate 100 kilowatts of heat, is something like 150 kilos. And plus all the cooling equipment and the high voltage generator, because we're working with extreme high tension. And so having this setup and the detectors rotating at, it used to be 2 rotations per second. Nowadays we can go to 3.5 rotations per second from a mechanical point of view, which is not really something we care about as people on the math side, but it's really an incredible feature. So even going from 2 rotations per second to 3, it's really complicated. Indeed, we have one, you can see an open CT scanner which rotates at clinical speed. Why is it moving? Okay. And it's should be accelerating a bit, but at acquisition speed, it's extremely. You can see this is like the whole setup that is moving is about half a ton, and it's spinning so fast. And you need to keep in mind that the detector, especially the detector, should not vibrate to dimensions of the resolutions that you need, because CT scanners, we'll see that in the next slides, but have a very high spatial resolution. So if the detector was vibrating by 1 millimeter, you will lose all of that. So it's, this is a quite hard technology, let's say. But, they managed to do that. So, how does the image reconstruction perform? works? It works using the Radon transform, the mathematical algorithm that I told you it was invented in 1917. This is the equation of the transformation, which basically means sum everything along the angle, in this case using theta as the angle, along the angle you are projecting to, which means you are working maybe along this, this line. I project along here, and I meet, let's say, zero things along the line, so my projection will be 0. If I do this here, I will have some more structure, so my integral will be higher. And if I go here, but here I have something of smaller intensity, my integral will be lower. So suppose to have an example image, two circles, one with higher and one with lower intensity, and I take the projections along multiple directions. I do it this way, and I can see the profile of one circle and of the other. If I do it this way, they are a bit superimposed. If I do it this way, they're perfectly separated, and this way, they're perfectly superimposed. So this is our, what we can call in mathematics, our forward model. Now you can ask yourself, how do I get back from the detector signal to my image? I can think about summing all the projections. You keep on doing this, but then you ask, okay, what do I do? Let's say that I acquired 180 projections, which are the complete set. But what I get back, given how I was proceeding, you can see that every time that I do a back projection, I get a tail along the whole image. So what I get is a very blurry image. It can be proven. Of course, this is not a course about reconstruction algorithms, even if artificial intelligence is really transforming reconstruction algorithms, so it's a really nice field. But it can be proven that analytically the solution is the back projection followed by some high-pass filter that removes all of this blurring. Now, this is the scheme. This is a transformation which is similar to the Fourier transformation. Actually, they are mathematically related. So you start from an image that you have. You take the Radon projection. This is what it looks like. Then you do the back projections. You get the blurry image. And then you apply a filter, which in a frequency spectrum is a ramp, which means that you're going to excite a lot the high frequencies. Okay, so we don't need it that much here, but this is something that we need to keep in mind. What happens here? What happens when we have noise? Because reconstruction, it's an ill-pose problem. Ill-pose problems are problems where a very little noise in the data drastically influence the variables that you want to fit. It's a concept not related only to imaging, but to the most diverse fields. And image reconstruction in tomography is this kind of problem. So we have that little noise in the data. Let's say we have this sinogram here, which is the name of what you get by the Radon transform. You have this noise here, which is, we will say it's not that much. And the reconstruction looks like this. This means that our reconstruction, our inversion of the problem, greatly enhances noise, and especially does that at high frequencies. However, high frequencies are what our vision, human vision, which is the complex of eye plus brain and processing and whatnot, is mostly focuses on to recognize objects. So this means that we really need to have as little noise as possible in the original data, and we really want to denoise the image that we acquire, because otherwise they hide the high frequency features, which means edges, which means small structures, small details, or patterns. Now, this is, I've shown you this in the previous lecture, and we said that X-ray are absorbed by different kind of tissues depending on their density, according to what is described by this table here. This plot here. And we have seen that these absorption coefficients depend strongly on the density of the tissue of interest. So this means that when we reconstruct an image, differing from planar X-rays, actually we have a quantitative unit. So we get images that are directly have a unit of measure. I didn't mention unit of measures with X-ray images in the previous lectures because they have none. They are like a pictures taken from a camera. Actually, we're using the same detector. So, I mean, we can say more white or less white, but this doesn't mean much. In CT, instead, they reconstruct an image which gives you then, pixel by pixel, the absorption coefficient. And we show that on screen using the Hounsfield unit, which is quite a trivial definition, which is the absorption of that pixel normalized by the absorption of water plus multiplied by 1000 for historical reason. This means that the lowest value you can have when the absorption is 0 is -1 times 1000, which means -1000. And so experimentally, all these kind of tissues have their own specific absorption coefficient. So lungs, according to the patient, the X-ray energy, and also the phase of inspiration, because when you are in full expiration, the lungs are more dense than when you are inspirating, so they are more filled with air. So it's between -800 to -500. Fat, which we said it's the least absorbing of fat is, it's the blue one. Fat is the least absorbing one, has -100. Water has 0 by definition, of course. Muscle has between 10 and 40. Tissue, like organs, are slightly more. And bones are the hardest one. And according to which kind of bones, they can go up to even 3000. What does this mean? We said in the first lectures that on screen you cannot, or even if you could, it doesn't really make sense, compress the whole intensity scale on the 255 levels of gray that a screen can show. So what the physicians do before reading the image, and reading is the technical term for producing the report, is to decide along which gray levels you want to read it. So if you want to take a look at the lungs, which have very low intensity values and very high contrast with surrounding tissues, you have a window that spans 1500 Hounsfield units. If you want to take a look at the brain, where the gray matter is slightly more dense than the white matter, which has slightly more fat, use a window which is 80 Hounsfield units large. And they are defined along a certain, the window is defined across a certain level. So we said the lung have an intensity of about -500, so you center your window around -600. the mediastinum, which is this part of the body, the part of the body in the middle of the lungs, where there is the heart, the coronaries, the aorta, the trachea is soft tissues, so you set a level of 50 and a window of 350. You will see in the notebook how to play with that and to see that you recognize different things when you set different windows. Any question? Okay. So to summarize the properties of the CT, it has a quite high in-plane resolution, which is it has a resolution of 1 millimeter, let's say. You can probably, the most novel CT scanner can go to 0.8 or something like that. But you need to keep in mind that we said that during the reconstruction, we have noise at high frequencies. So you exploit the full resolution of the scanner only if you need that, because otherwise you will need to suppress noise. And to suppress noise, you need to give more X-rays to the patients, which are bad. The thickness, instead, which is of this slice, which goes along the third direction, which is the head to feet direction, is actually user selectable. It can be as low as 0.6 millimeters, but if you do not read all that resolution to save radiation dose, you can select a 5 millimeter slice thickness. Generally, it's 512 times 512 image sites. Latest scanners, which do not have that many memory concerns anymore, can go sometimes go to 1024. They are able to reconstruct a radius of 50 centimeters, a diameter of 50 centimeters. The pixel size that we use goes from 1 millimeter to 0.5 millimeter. And we mentioned the rotation time, which is between 1 second to 0.3 seconds. Now, if you are rotating at 0.3 seconds and acquiring a 4 centimeter slab of the body because you have a multi-slice CT, this means that you can go from head to feet in, I don't know, like 20 seconds or so, I don't remember anymore, which means that this exam is extremely fast. However, one issue is that the amount of contrast that we have, and contrast again is what allows us to differentiate things, not only us, but even automated algorithms. If we have a flat surface of a uniform color, no algorithm can distinguish anything there because there is nothing there. So as you can see here, it's we have lungs, and in the lungs you can see the inside structure really, really well. We have some examples later. But in the tissues, we can't distinguish much of what's going on there. We have a bit of contrast here between the muscles and the fat. And there on top we have the liver. If you have it on your screen, probably you can see it a bit better. You can see something, but not that much. So the way that this can be improved is by using what's called contrast media, which is a molecule with the properties of moving with the blood. It's and so and doesn't do much biologically. So you get these molecules which just stay in the blood. You inject them, but in these molecules there is one atom which has a very high X-ray absorption probability. So you see where this molecule is going. You inject it in the blood during the scan itself, and you just take images and follow what's happening. And here I just took from Wikipedia the so-called phases. So as this molecule does a single pass with the blood, the first thing that it does, it moves, it stays in the arteries. And so you can image the vessels, the large vessels and the arteries. There it goes in the lungs, in the pulmonary phase. Then it starts moving in the veins in the late phase or in different kind of venal phase. And finally, if there are some broken capillaries or some structures with angiogenesis, which means creation of new very small vessels, which is something that can happen happens often with tumors, for example. You see the contrast media remaining there after minutes, which is after all the flow has passed. And so this can help a lot with the diagnosis. If you are interested, you can go on Radiopedia, on Wikipedia, or so on, and see for different kind of illnesses how you can use contrast media. So let's get a recap of what are the properties of this methodology. And like we did with X-rays, the fact is that it can see the same kind of contrast as planar X-rays with lower resolution, because we are using a resolution of 1 millimeter and not 100 microns. But we see that in 3D, so we see structures really better because they don't have shades in the front or in the back. With contrast media, we can highlight really a high number of pathologies. It shows gross anatomy mainly, because it mostly shows just the boundaries of the organ, because the organs are soft tissues, so they're mostly uniform inside. But generally, we have a layer of fat between one organ and the other, so they can be very useful to plan operations. The pros of this methodology is that it's relatively cheap, not like 10 euros a scan as for a thorax X-rays, but without contrast media, a single scan can be 100 euros or 150. With contrast media, it depends a lot on the number of sequences that you get, because as we stated, you just put the patients on the table, then you acquire an image, then you can inject contrast media and acquire a sequence in the arterial phase, then you can do a second one, and each one increases the cost, also because it takes time to read them. It's also a super fast technique. As we said, you can acquire a body scan from the head to the feet in seconds, probably less than half a minute. It's highly tolerable. It has no side effects. Even contrast media can cause some issues in patients with reduced kidney functions, but amongst all the drugs that we use, when you're doing a CT scan, you might inject 50 grams of the drug, which is the contrast media, in half a liter of water. Which, if you think about all the other drugs that you might ever take, which have a safety limit of 1 gram, 2 grams, 50 grams, which is like 3 spoonfuls, which means that it's super tolerable to the body. A CT scanner can cost maybe the most advanced one, 2 million euros or 1 million euro for a routine one, and it lasts many years, so it's more than a decade. So the cost is mostly the team that needs to operate it, because to acquire a scan you need a physicians that do the reading, and in Italy it also needs to be present for legal reason, a technologist that operates it, and maybe a nurse if you need to do contrast media injection. And this team can work only 8 hours per day. The CT scanner generally works 24 hours per day, or sometimes 12 hours. So the cost of the personnel is much, much more of that of the scanner. And given that it's so fast, so easy, and so on, it also has lots of applications for emergency medicine. Because if you have a brain stroke with this 20-second scan, which can also be performed on someone immobilized with all the tools from the emergency room or the venous line, from 1 minute when you have positioned the patients, you know if it's a stroke or an hemorrhage, which have opposite kind of treatments. So if you have what's called a polytrauma, which like a car accidents where some people got badly hit, but you do not know exactly what's broke. You do a CT scan and you know if there are internal bleedings, which are not visible from the outside. So it has lots of application. And we can see that it will contrast with MR, which is not suitable for emergency applications. The bad part of these scanners is that it has a relatively high radiation dose, especially if you do multiple sequences or if you want to do follow-up every couple of months. It's not really feasible. And it has a limited power, meaning diagnostic power, given that by visualizing only density information, or if we are lucky, density plus contrast media in the blood, there are a number of things that cannot be seen. Now, some example images. This is what you see in the lungs. CT, as I was mentioning, given that it sees density and modification in density are super apparent in lungs. This is an interstitial pneumonia, which was also what was happening in patients with COVID, but also with other pathologies. You can see that between the alveoli, the density changes a huge lot. You can also recognize this emphysema, which appears as a bubble. Without contrast media, this is what you see in an abdomen. All the black here is the abdominal fat. The black here instead is the visceral fat, which is essential. It's something that you get when you go, if you are a bodybuilder and you go too low in body fat, and you start losing that once the organ starts to have troubles. And I was saying before, we can recognize very well organ boundaries, like kidneys. This is the intestine, all of that. This is the aorta. But we don't have much on top. We don't see much on top of recognizing the boundaries of the organ. The only clinical finding that we can have here in this case are renal calculi, which in the kidneys, which we can see easily because calculi contain calcium, and calcium is radiation. It's very hard to X-rays. So this is an example of what you can do with contrast media. This is the liver without in a phase with little contrast media, and it appears uniform. Instead, with contrast media, you can see both all of the contrast media in the veins and also two masses which are otherwise not recognizable. Then you can see also the contrast media in all other organs, and here you still have a bit in the aorta. Okay, that's all I had to say about CT. If you have any questions. There is another slide when you download it with a link if you are interested in how they encode spatial coordinates in the image. Because for multiple reasons, it can be interesting to reconstruct exactly how where in space every pixel is, and also how the patient is oriented. I mean, when you're taking a look at the abdomen, it's pretty obvious what's left and what's right, even if it exists the so-called C2 inversu, which is a prevalence of about 1 for every 100,000 people, which means that all internal organs are flipped left to right. But anyway, here you can recognize if you are high or low in the abdomen or whatnot. But like if you take an image of the brain, you cannot recognize from the image where is the left and where is the right. So it's pretty useful to encode that. Okay, if you don't have any questions. I have sorry, let me change the screen. Now, I have uploaded on the Google Drive a course from a freeware course from another university, which you are free to refer to, and which I will use the part on MR, which is very, very complicated. So it's not as intuitive as CT, sadly. In fact, when I was working in the hospital, I was always discussing with other physicists that we cannot understand how it was discovered, how they invented the devices, but it's really an amazing methodology. So let's start with magnetic resonance. We will not see the principle of image formation, but we will just take a look at which kind of contrast we have. We'll start from the nuclear magnetic resonance effect. So this is how the scanner looks, and it includes, it basically is a huge magnet, super strong magnet. We will have some details about what we mean by strong. This is generally, well, nowadays it's standard, it's not generally, superconducting magnets. So it's an electromagnet. The magnetic field is generated by a solenoid where lots of current is passing by, and you cannot achieve that using normal cables. You put superconducting cables refrigerated by liquid helium at a temperature of minus 270 degrees, which is 4 degrees above absolute zero. And at that intensity, electric current can keep on flowing without opposing any resistance, any electrical resistance. Now, what are the interesting part of MRI? That it has no ionizing radiation and that it can generate lots of different types of contrast. This is really what makes it so interesting in medicine, and by the way, not only for clinical applications, but in psychology and in behavioral economics, they use MRI to study brain responses to external stimuli, given how many different kind of things it can see. It also provides a lot of soft tissue contrast. We said before that all soft tissues, which are organ, muscles, and whatever, in CT look kind of the same. Instead, in MRI, you have different parts of muscles looking completely different. And in CT, also it has many other cool properties, like that you can acquire images in almost arbitrary orientations with as good spatial resolution as CT, or even more probably. But the scan time is generally quite long. This is just to give you an example. This is what you see in CT. And in the ER, you can see something in the brain if there is a stroke or a hemorrhage, but that's pretty much it. In the brain, just with the two common kind of MR contrast that you can acquire, give you some visibly different kind of contrast information. So what's the magnetic resonance effect? We start with an example of a compass, the needle that always points north. So what happens if it's not pointing north? It starts moving north, but it gets an acceleration and it goes the other way. It goes too much in the other one. Then it starts flipping back, and so it starts oscillating. In an actual compass, there is some damping mechanism, so it stops oscillating pretty fast. However, given the mathematical properties of the pendulum and the harmonic oscillator, it means that the frequency at which it oscillates is always the same, independent of how much you flipped it and things like that, as long as the magnetic field is the same. So what happens if you send a radio frequency wave? Radio frequency waves are the one used by radios, TVs, Wi-Fi broadcasting over the air. We mentioned them in the last lectures. Also, X-rays technically are electromagnetic radiation. But here we're talking about 1 meter, 1 to 10 meter wavelength instead of 1 nanometer wavelength. So it's pretty different. If you send an electromagnetic pulse wave of the same frequency of the oscillation frequency of this harmonic oscillation of this compass, which is an harmonic oscillator, it starts resonating and moving in the same way at the same frequency. However, an oscillating magnet is also a source of radio frequency waves, which you can detect with an antenna. Given the properties of antennas, by the way, they can be used both as a transmitter and receivers. So this means that you can send a wave at the resonance frequency. This compass starts oscillating and it emits a wave at the same frequencies, which you can then detect with the same antenna that you use to send the wave. There is also a tool if you want to play with that. Now, the magnetic field can be produced by electrical currents or magnets. It is a vector field, which means that it's specified by a magnitude, of course, but also by an orientation. It goes, conventionally, we say that the magnetic field goes from the North Pole to the South Pole. So if you have a magnet, the magnetic field around it will behave this way. The unit of measure is given in Teslas, and the Earth magnetic field, which is enough to turn the compass, is in this unit 6×10⁻⁶. While for MRI, the fields we use are from 1 to 3 Tesla. For pure research application, because this starts to have impacts on the body, we have also 7 Tesla, or even up to 14 Tesla for chemical specimens, not for living humans. Or from some orthopedic applications, you can go slightly lower than that. You can also go to 0.5, which is cheaper to build. But anyway, we are talking about 1 million times stronger than the Earth magnetic field. Now, what is it that it's resonating in the human body? Hydrogen nuclei. Why? Because they are magnetic. Not all nuclei are, only some. And hydrogen has the very good property for us to be the most common element in the body. We are made mostly of water, and water has 2 atoms of hydrogen. The next other things that we have in the body is things made of things made of organic chemistry. So like hydrocarbons, which means carbon bound to hydrogens. This is fat, this is proteins, this is really 90% of what we're made of. So we have really lots of hydrogen in the body. Here they estimate 10 to the 27 nuclei. Other nuclei that can resonate, which we have in the body, is fluorine, fluorine 19, but that's something of which we have I don't know, like 10 to the 20, so much less than 1 million times that. So the signals will be less interesting, less strong. Now, hydrogen nuclei, as we are standing here, are randomly interacting in the body, and so their magnetic orientation is pointing in a random direction. Therefore, if you measure the magnetization of your body, it will be 0, because if you sum really a huge number of random vectors, of randomly oriented vectors, the sum is 0. If you apply a very strong magnetic field, the nuclei starts to align along the direction of the magnetic field. Due to some quantum mechanic effect, actually they don't all point in the same direction. It will be a majority of them, and many others will point in the opposite direction. But the net magnetization, so the sum of everything, because of course we are looking at, even if you're looking at voxel of 1 millimeter, in 1 millimeter you have the number of Avogadro, 10 to the 20 nuclei. So the averaging is really a lot. You don't care about individual nuclei anymore. So we have the net magnetization, which starts to behave like our compass, and it is rotating or moving along the direction of the big magnetic field B0, and gradually it aligns that way. This is the equivalent to the compass needle. The frequency of precession is due to classical electromagnetism law, due to the magnetic strength of your magnet, in this case the hydrogen nuclei, and the strength of the magnetic field. Combining that, we have that the precession frequency is 42.576 megahertz per Tesla, which means that in a scanner, which is 1.5 Tesla, you have 80 megahertz, or 120 in a 3 Tesla scanner. And the FM radio that we used to have in our cars before DAB system, it was 100 megahertz. So we're talking about the same wavelength and the same frequencies of FM radio, just to give you an idea. Which, by the way, given that you don't only have FM radio in the air, but lots of other things, and the Mars scanner has to be built in a shielded rooms, shielded from every single possible source of electromagnetic interference. Now, we have said that we can push our magnets with a radio frequency wave of the same frequency of the precession frequency out of its stable position. Therefore, what they invented was to send radio frequency pulses orthogonal to B0, because you want to flip the magnet, at the resonance frequency F. Therefore, if you send these, when you do that, all the spins starts rotating in phase between themselves around B0. So when you're looking from outside, if this is the direction of the magnetic field, this is the direction of the field B1, which is rotating at this resonance frequency around B0. You have that before excitation, the net magnetization M is pointing in the direction of the field, and after the excitation, it's rotating around it instead. Now, if you start moving together with the atoms, you will see it as standing static. I don't know if this simplification helps or not, but whatever. Now, what happens after you have flipped the net magnetization? It starts to go back to where it was before. The spins starts to realign with the main magnetic field. This relaxation process is the origin of the image contrast in MRI. the speed with which this happens depends on the tissue, and therefore it allows to differentiate the different tissues. Now, we have talked until now of the net magnetization. What we are interested actually is the net magnetization in a defined volume. So we will divide our volume in pixels. The way in which we are able to reconstruct which is the net magnetization in each place is not something which we will cover because it's something that takes like 6 hours, sadly. But this is the concept of what we will do. Now, to recap, we assume that B0 is aligned with the z-axis of some coordinates system. We split the magnetization per voxel into components, one parallel to the main magnetic field and one perpendicular to that. Initially, the net magnetization is this way. The perpendicular one is 0, and the net magnetization is maximal. After the excitation, the effect is the same. Sorry, it's the opposite. It's 0 along the main magnetic field and maximal in the other direction. You need to keep in mind that when we have this signal here, sorry, this magnetization here, this one is rotating at the resonance frequency, so it's emitting a signal that you can detect with your antenna. While when everything is aligned with the net magnetization, you can't see anything anymore. You don't have a signal anymore. Due to physics, to some weird quantum physics, we have the two magnetization starts to behave differently. And we have two processes. We have the recovery of the longitudinal component z, which takes one time, and you have the decay of the transversal component xy, which is much, much faster. So if you measure the longitudinal magnetization, it will behave like this. It's an exponential phenomena with a characteristic time which we will call T1. So after the excitation, it's 0, and it starts to increase with its in an exponential way with a characteristic time T1. This T1 is tissue dependent, so we are able to generate contrast. The reasons is the transfer of the received energy into the surrounding lattice of atoms, and this is just for your knowledge, whatever, how this might help. Oh, by the way, we've seen here it's writing 2.5 seconds, just to give you an idea of what's the average scale. The transversal magnetization instead has an exponential decay, and it's characterized by a specific time which is called T2. And again, also this one is tissue dependent. This one is attained assuming a perfectly homogeneous magnetic field. And the reason and the cause of this loss of signal is that the interaction of the magnetic field of each nuclei causes this huge number of nuclei to start precessing at different, as microscopically different frequencies, and so they start to lack coherence. They don't have the same phase anymore. It starts to behave randomly and not coherently, and so the signal decays in this plane before it reappears on the other plane. Instead, here they choose as an example time 45 milliseconds compared to the 2 seconds that we were talking about, 41. On top of that, we have some non-idealities in the real world. So the magnetic field is non-perfectly homogeneous, which worsen this phenomenon, and there is also a so-called T2 star, which is always smaller than the true T2 of a tissue. So this is what you see before relaxation. You have a net magnetization, which starts to decay much faster than it reappears along the z-axis. How do we exploit them? When we acquire a signal, we can modify on our scanner two parameters. The echo time, which influences when we are going to read the signal, the transversal magnetization signal, and the repetition time, which is the time between two subsequent excitations. So what we do is called a sequence, because we repeat this operation hundreds of times to acquire the signal. We have an excitation, and after an echo time, we do the reading, and after a repetition time, we do another excitation. This leads us to the weighting, to how we achieve what's called weighting. Okay, so here, this is an example of what's called a T1 weighted image. To get we say not a T1 image, but a T1 weighted, because we mean that it's not a map of how much the T1 value is in every pixel. We just mean that it's something which is mostly influenced by T1, so it's not quantitative. It's also possible to get quantitative T1 maps, but they don't have a clinical use. So suppose that you have two tissues with some T2 and some T1. If you want to have a magnetization, an image which is influenced mostly by T1, you need to take a time of echo, which is the measurement, as short as possible, so that differences in T2 do not show up in the image, because if you acquire at a T echo much, much shorter than T2, the decay will not have happened. But then you use a repetition time which is slower than T1, so that in the second, when you are doing the subsequent excitations, the tissue with longer T1 has not recovered the full magnetization yet, so it will be less excited, so it will give you back less signal. And in this way, you get a T2 weighted image, a T1 weighted image, sorry. It's the opposite to acquire a T2 weighted image. You do excitations at a repetition times much longer than T1, but then you read at a T echo which is similar to an average T2, which means that tissues with T2 shorter of that will have fully decayed, and you see that them as black, while tissues with much longer T2, well, it will be slightly longer. It won't be much longer, because they all in a range between 20 and 60 milliseconds, not 10 to 1000. And in this way, you can see your image is influenced a lot by the T2, but not much by T1. Again, like in the previous case, what we have is an image which is mostly influenced by T2. It's not a map of T2 values. It's not quantitative. There is also another possibility. You can have, we had before, short TR and long TE, or long TR and long TE. There is a third possibility, which is what's called proton density weighting, which is long TR, so you don't have any contrast due to different T1, and short T echo, so you don't have contrast due to T2. So what you get the number of hydrogen nuclei, or the number of hydrogen nuclei. This is generally the least interesting contrast, and this is why it's called the proton density weighting, because it's influenced exclusively by the number of hydrogen nuclei there. This is an image again of the brain. We have a little contrast, but we can still see something, and basically is how much water these three different kind of tissues have. Indeed, we don't see much contrast between the gray matter and the ventriculi, which is, this is a cavity full of water, while this is gray matter. So this is the last slide about MR, which I understand to be quite hard. And this is what we have. We have the three combination of TE and TR that you can have. To recap, if you have short T echo, you can achieve with short TR, T1 weighting, or with long TR, proton density weighting. If you have long TR and long TE, you have 2-2 weighting. The missing combination, if you have short TR, you are not going to have a very strong excitation because of the short TR. And if you have long TR, therefore if you have low excitation, you have also low signal. If you have long T echo, the signal will also have decayed, so you will have very weak signal to start with, so there's not much to see. And also, it's not clear which kind of what the image could be influenced by, so it has no clinical applications. Okay, and we will see in a very quick overview in the next lecture that MR is one of the most complex way to do imaging, which can really see the most disparate things if you are creative enough with your reconstruction algorithms. But these are the basic of all the images that you can get. And I know that sadly it's the least intuitive medical imaging modality, so it's not an issue if you don't understand the technical details. So do we have any questions about that? For now, if you want to reflect about that and do questions, ask questions in the next, on Monday. Now, I will, if you are interested, what I will do now, we still have 20 minutes about. I just made a Python notebook. Yep. This is my computer, not the drive. Just to see how you can read the DICOM volume, and you can display a volume and display a CT with all the peculiarities of a volume and the CT windowing effects. This is pretty easy. We will use PyDICOM like the other time. Now, one thing that you need to keep in mind, no, I mean, you don't need to keep this in mind, I'm telling you right now, it's that DICOM images for volumes often are exported as a series of files. So you don't have a single file with your 3D volumes, but you have, this is a CT, so probably some hundreds, 310 files, which you need to read in a sequence, and then to stack them in a correct order. It takes 2 lines of code. That's not really an issue. But this is just to let you know. And also, I've mentioned that we have a scale. So when reading the data, When reading the data, you need to correct, I've written this in the instructions, for a scaling factor and an offset factor to convert the raw data, which are saved in an integer format, into float numbers or in the correct scale. Then the task to do is just to try taking a look at the image with the correct aspect ratio and trying different imaging windows. So it's pretty straightforward.